our side?
We're just waiting for one person. There's the person.
Okay, now.
Okay.
There's a way to shut off the static on the...
Yeah. Can you guys mute the mic?
Yeah.
We don't want to hear your heavy breathing. Okay, great. Right, thanks. It's my pleasure to introduce Lindsey Kuper, who's currently a student at Indiana University. She, once upon a time, was working for a bit with Amal Ahmed, and she's switched now, and she's working with Ryan Newton on some very interesting work with deterministic parallelism.
Thanks, Derek. So as Derek said, I'm Lindsey, for those of you who haven't met me, and I'm going to be talking about the work that I've been doing for the last year and a half or so on lattice-based deterministic parallel computation. And this is work done in collaboration with my advisor, Ryan, at Indiana. And so as I was getting ready to visit here, and then also this week, I spent some time looking at the web pages of various people in the group here to get up to speed on what you were all working on, and I have come to the understanding that a few of you, and Derek in particular, are movie buffs, and that we like some of the same movies and directors. And believe it or not, this is actually relevant to my talk on deterministic parallelism, because when programmers have to contend with unintentional non-determinism in their parallel programs, they're really entering a world of pain. And what I mean by that is, as an example of that pain, so here's an example of a program written in a tiny hypothetical programming language, the most interesting feature of which is this let par form, which lets us do parallel evaluation of multiple subexpressions. So what's going on in this program? Well, on the first line here, we're writing the value 0 into a location L, and that's what put L0 does. And we're doing this just for effect, so we don't care about the return value of put L0. That's what this underscore is. And then we have the let par. So here, in some order, we're getting the value out of L, and we're putting it in the variable, writing it into the variable V. And then we're also writing 8 into L, again, only for effect. And then finally, the whole thing evaluates to whatever the value of V is at the end. So what does this program evaluate to? Well, we don't know. It could be either 0 or 8, depending on the whims of the scheduler. So the way we're going to define non-determinism for the purposes of this talk is a non-deterministic program is one where the observable output could be different on multiple runs, depending on what the scheduler decides to do that day. And I emphasize the word observable because observability is going to kind of be a theme of this talk. But that definition of non-determinism should kind of make you sit up and take notice because it depends on a notion of what's observable. And in particular, the only thing that we're going to be observing is the value at the end of the run of the program. So for instance, we're not going to be observing if these individual subcomputations in the let par were printing messages as they went along. That wouldn't be part of our definition of non-determinism. And I kind of, the way that I like to think of this is every program is non-deterministic in some sense, right? Because programs are going to behave differently by some metric. If you're running it on a real machine, it might take different amounts of time to execute on different runs. The processor might produce different amounts of heat. There are different notions of what's observable and not observable. But in this setting, even with this very, very limited amount of information that we're allowed to observe, which is just the value at the end of the run, even in that case, this is a non-deterministic program. So our goal is going to be to come up with deterministic, by construction, programming models which only allow us to write deterministic programs. And so the goal will be to come up with a model of parallel computation in which a program like this is either just rejected or forced to behave deterministically. So this is not a new idea, and there have been a lot of deterministic parallel models over the decades. And one of the traditional ones is what's called a single assignment model, in which you disallow multiple writes to locations in the store. So this program would be rejected under a single assignment model because we're trying to write to L twice. And as I said, this isn't a new idea. The first reference that I can find for a single assignment is this Tesler and Ania paper, 1968. And they had a language called Compel, which was short for compute parallel. And this was the earliest single assignment language that I'm aware of. But this has popped up in all kinds of deterministic parallel models since then. In the 80s, in the work on the id programming language, there was work on I structures and specifically Alvars, which are single assignment variables that have a blocking read semantics, which means that they can be either empty or full with a value. And if you try to read from them at the time that they're empty, then you're not going to be able to do that read until they're populated with a value, at which point the read will unblock. And these Alvars have turned up in other settings. They've been in concurrent ML. They show up as the foundation for the work on monad par, the monad for deterministic parallelism work that was at Haskell Symposium a couple of years ago, and countless other settings. So it's a popular technique, and it works. So under this model, programs are deterministic by construction, and even in the presence of shared state. But we're not satisfied with this, because the single assignment model rules out some deterministic programs that we might like to write. So just as the simplest possible example of such a program, what about a program where you try to write the same value into an Alvar twice? And so this program is obviously deterministic, right? Because regardless of when that read from L happens, the value is going to be 3. So this program is always going to evaluate to 3, but it would be ruled out by the single assignment model. So in other words, the single assignment model is not complete. There are some deterministic programs that you can't write in it. As a slightly more sophisticated example, so take for instance a setting where the variable is a pair. And this time, we're doing 2 writes into the variable, but we're writing different components of the pair. And this is just some notation I made up, meaning that, so 4 comma bottom, it doesn't mean we're writing a value called bottom, but rather it just means we're writing 4 into the first component of the pair and ignoring the second. And then likewise here, we're writing into the second component of the pair, 3, and ignoring the first. So this should be deterministic because those writes are, they don't overlap. So regardless of the order in which they happen, we should get 4, 3 out here at the end. But again, this wouldn't be allowed under the single assignment model. And you could argue that you could implement this by having each of those components of the pair be a separate Alvar. But nevertheless, this wouldn't, that would be a way of faking it, but this, writing this directly wouldn't be allowed. So as an example of the kind of program that you might not be able to write using Alvars alone, and this is using liberal use of syntactic sugar here, but so suppose that you had a trie in which the keys were strings of bits, and you wanted to do 2 insertions into this trie. So suppose it's empty right now, and you want to insert 2 keys, 1111 and 1100. So if you were trying to implement this trie out of Alvars, then the order in which you did those insertions, you wouldn't be able to do it because they have to share a prefix of 11. So one of the subcomputations in the let part is trying to write 1111, so going down the I guess the left-hand branch of the trie. The other one is sharing a prefix but then branching off the other way. So these unify with each other in a sense, so they should both be allowed, and you should be able to, the order of them shouldn't matter, but if nodes are implemented out of Alvars in this trie, then you wouldn't be able to do it because of the single assignment restriction. So these are examples of deterministic programs that you can't do in a single assignment model. So we were hoping to come up with something a little more general. And so in the process of trying to figure out how to do that, I started thinking about, well, what is it that makes this model deterministic? What is the essence of determinism in this model? And so, and that's kind of brings me to the next part here. So as I mentioned, single assignment is an old idea, but I'm fairly new to this research area. So I first encountered it actually in this 2010 paper about this system called Concurrent Collections, which is, it's actually a product that Intel released, and it's a system by which you can write sequential deterministic programs, and then the concurrent collection compiler will compose them into a deterministic parallel program. But under the hood, it's a single assignment language. And in this paper, they give a kind of a featherweight calculus for the concurrent collections language that they give a proof of determinism for. And what I noticed when I looked at this little language and this determinism proof was that the notion of determinism was based on this notion of monotonicity. And so that was really interesting to me. And so monotonicity is a concept that we're probably all aware of from Calc 1, but I'll go back to it. So in your Calc 1 textbook, in a former life, you probably saw a picture that looked something like this, of a graph of a non-decreasing function going up and to the right. And so we can generalize that idea of monotonicity to the more general setting of order theory, where we say that a function is monotonic if and only if, given a particular partial order, if you have some two elements that have an order in that partial order, x and y, then f applied to x turns out to be less than or equal to f applied to y. Or in other words, f preserves the ordering. So in the setting of thinking about languages, you can think of this monotonicity idea as an order-preserving mapping between ordered sets. So for instance, like in the concurrent collection setting, one of those ordered sets is going to be just the sequence of evaluation steps, or rather the sequence of configurations that a program is in as it evaluates. So that's obviously an ordered set, right? Because it's a sequence of configurations. And then the other ordered set is the states that the store can be in as the program goes along. So, and that's the order there. They mentioned non-decreasing domain here. So because the language is single assignment, you can only assign to variables once, and so the domain of that store can only grow. They call it a data collection, but it's a store. So there's an order-preserving mapping between one of those ordered sets and the other one, and so that's really what enables determinism in this language. So I thought that was cool, but then.
Oh, sorry. Can you go back a second, just to be clear about it? So
Yep.
what's in this example? Well, yeah, this slide.
Yep.
Yeah. So what is the function that's monotone?
So in this case, because the store is part of a configuration, so a configuration is the store and then like whatever, this is not an expression language, but it's whatever command is being worked on. So in this case, the function, I guess, would just be the function that kind of pulls the store out of that configuration. When they say this, I know this is confusing because they're talking about the store being a partial function, but I don't think that's the function they're saying is monotonic. I think they're saying the monotonic function is the mapping between the set of configurations that the program can go through and the set of states that the store can be in separately. And then you find that set of configurations that the program can go through.
I'm just trying to map this into the formula you had in the next, into the definition of monotonicity you had.
Yep. So
on the next slide, that's what I mapped it. Confused about.
Okay, so the actual function being computed is in that
what
case,
are the ordered sets? Maybe I should start.
Okay, so one ordered set is the set of configurations, the sequence of configurations that a particular program goes through as it's being evaluated.
Okay, so the ordering then is if A is less than or equal to B, if A step star to B?
Yeah. Well, yes, yeah.
Basically.
Right,
Okay.
right.
Okay.
And you can kind of see that here. So
you basically have
Yes, right.
identity function, but two different orders. I guess one in domain and the other in codomain. So.
okay, so
I see. So you're saying the function just pulls out the store from it?
yeah. There might be another monotonic function here actually. I think there's actually like two notions of monotonicity in this language, but that's the one that I was thinking of. So that was one example of a language that exploited monotonicity for determinism. But then I went to look at this other paper, which is about one of the classic models of deterministic parallel computation, and this is on process networks. And this is the original paper on KPNs from Gilkhan in 1974. And well, this paper is about a deterministic parallel model that's kind of drastically different from the other one in that it doesn't have any shared state. A Kahn process network is kind of this beautifully simple model where you have a bunch of independent computing stations that are each computing serial deterministic function. And they're allowed to communicate with each other, but the communication is limited. They can only communicate along these first in, first out queues with each other. And but the determinism of this system also turns out to be...
Do you mind if I turn the lights off?
Oh, by all means, yeah. So the determinism of this system also turns out to have something to do with monotonicity. What is actually really cool here is that the parallelism in this system is because of monotonicity also. And the reason for that is that it allows pipelining in the sense that if I'm a node in a con process network computing a function and I'm getting input from Aaron and doing some computation on it and sending it out to Scott, well, if Aaron gives me some piece of data and I compute on it, well, I don't have to wait to receive the rest of the data from Aaron in order to finish computing and hand it to Scott, because I know, because of the monotonicity guarantee, that whatever I compute and give to Scott is going to be a prefix of what I'm going to eventually compute and give to Scott. So in this case, the monotonic function is actually from the history of the input I receive to the history of the output that I produce. And so it's interesting because, so Kahn pointed out that this enables this sort of pipelining where I can start working on incomplete input. But he also sort of, he mentioned that it was a limitation, that the setting was deterministic. And then later other people went on to, as I learned when I was at Popple this week, other people later went on to generalize KPNs to do non-deterministic computation. But determinism was an aspect of this early model. And so this kind of made me think, with this monotonicity, or rather, determinism was a key aspect of this early model and kind of paired with this monotonicity. And it made me think that maybe, with this monotonicity idea popping up in these, at first appearing to be so different settings, that maybe monotonicity is kind of one of the keys to deterministic parallelism. And so this slide used to say monotonicity causes deterministic parallelism, and I'm not willing to go that far anymore. I'm sorry about the lights.
I'm even more sorry about the lights.
So this used to say causes, and I'm no longer willing to say that, because that's sort of like saying monotonicity is sufficient for deterministic parallelism. And I don't think I want to say that, but I think I do want to say that it's necessary. Because certainly, if a KPN were allowed to compute a non-monotonic function, for example, then you could introduce non-determinism all over the place. So what we decided to do was kind of take monotonicity as our beginning principle to try to build a deterministic parallel system that was more general than the single assignment one that I was showing you.
Wait, so what notion of monotonicity are you talking about now? Is it about the configurations?
So I'll show you, actually.
Okay.
So what we ended up doing was generalizing single assignment languages to parameterize them by a user-specified partial order. So, and now what we call our variables now in our language is Alvars, which is short for lattice variables. And an Ivar, the single assignment variable that we were talking about before, just turns out to be a special case of an Alvar. So here on the left, for instance, this is pretty much the simplest Alvar that you can have. And so it's a single assignment variable. It starts in the bottom state. And this one happens to be a natural number valued single assignment variable. So you can assign to it once, which moves you up in the lattice to the middle row. And then if you try to assign to it again, you go to top, which would be an error. So that's kind of the simplest example. But then in the middle here, we have, and this is kind of like the pair of 3 and 4 example I was showing you before. We can also do a lattice of pairs of Ivars. And here, you can kind of get an idea of what's going on by considering, for instance, the 0, 1 in this lattice. So there are 2 ways to get to 0, 1, right? You can write the 1 first, or you can write the 0 first. And both of those converge at 0, 1. In fact, it's the least upper bound of those 2 writes. Or so if you were to do those writes in either order, that's where you would end up. But we can also do things that aren't just constructions of Ivars in our system. So we could parameterize by just the natural number, the usual less than or equal to partially ordered set of the natural numbers starting at 1, and we could just have a monotonic counter. So anything that forms a joint semi-lattice is okay. And it has to be a joined semilattice, which is one where you have all least upper bounds, because we have to take least upper bounds in our semantics. We don't really care about greatest lower bounds, so it doesn't have to be a complete lattice. But I'm just going to use the word lattice to as an abbreviation.
So the counter is not limited to single assignment, right? I mean, there.
That's right. That's right. Yeah.
But the other ones are.
Right. Well, so you can do 2 assignments to a pair, but they have to be to the 2 components. Yeah. So yeah, the number of you can kind of see like the number of layers in the lattice are the number of assignments that you can do. So you could assign to this one infinitely.
Yeah.
Okay. So.
And one more question.
Yeah.
So,
Yeah.
How do you generalize this to tuples of arbitrary arity? So this is just 2. So.
Of arbitrary arity. So a lattice that.
Lattice would be like.
That's an interesting question, and I mean, obviously, you can generalize it to any fixed size record, right? But I hadn't thought a lot about arbitrary arity. I don't know if it forms a joint semilattice, then you're good. But I don't know. I hadn't really considered that case.
Well, what do you mean exactly by arbitrary arity?
So I mean, in this case, we just have tuples, just a x and y coordinates, let's say. So now, if I have n dimensions. So lattice would grow exponentially, right? In that case.
Sure, but
so if you can write down an ordering, then you're fine.
I mean, it might be hard to write on the board. But
Yeah.
perfectly reasonable mathematical definition.
When we were working on this the other day in Aaron's office, we found ourselves writing this little lattice so many times that we made up a notation for it because it's a pain to have to write these things down all the time. So anyway, so these are just 3 kind of examples of lattices that you could parameterize our system by. Scott, I don't know if I answered your question yet or not, so should
not
I?
quite, but just keep going.
Okay, I'll continue and maybe we'll see if it gets answered. So I want to kind of focus on this middle one for a little while because it's a good way to illustrate one of the other interesting aspects of our language. So as it turns out, just doing monotonic assignment according to the specified partial order is not enough to maintain determinism. We also have to tweak the way that we do reads. And this kind of makes sense. If you can imagine in the single assignment setting, you can only write to a variable once, right? But you're allowed to read arbitrarily the exact value of the variable as many times as you want. So we tweak the knobs differently. We allow more leeway on writes, because you can now do these monotonic writes. But in compensation, we have to turn down what you're allowed to read. So, and that's how we came up with this notion of what we call threshold reads. And so, what a threshold read is I think of it as sort of like a tripwire across the lattice. So when you're reading out of one of these Alvars, you're not allowed to get exactly the value that's in there. But this is where the notion of observation comes in again. You're allowed to make a limited observation of the actual state of that Alvar. And you do so by, when you do your read, when you do a get, you pass in an extra argument to the get, which we call a threshold set. And so this is an example of a threshold set here. This get second subset of the lattice that's appearing boxed in red here. So what's going on here is we only are interested in reading the second element out of a pair, and so whatever read that we do, it better be the case that second element has already been written. But we don't really care if the first element has been written yet. It might be there, it might not. So these boxed elements here, they form a sort of tripwire going across the lattice where if we're reading from something, or when we do our read, the state of that Alvar either has to be in that boxed set or it has to be above the elements in that boxed set in the lattice.
So it's a set of prefixes of the value that you're interested in.
A set of prefixes of.
I mean, is it a set of prefixes of the top? Oh well, hang on.
Sort of lower bound, yeah.
Yeah, it's a lower bound. And then this controls the information that you're allowed to read out of the variable. So as I said, you can make a limited observation, and in fact, the observation that you're allowed to make is going to be a lower bound on the actual state of that Alvar that you're reading from. And in fact, what you're going to get back when you do a get into such a lattice is a single value that is the unique element of this threshold set, this boxed threshold set, the unique element of that set that the actual value of the lattice is at or above. And the reason why it'll be a unique element of that set is because there's a condition on these threshold sets, which is that for all pairs of elements in the threshold set, the least upper bound of those two elements has to be top. So you can kind of see that happening here, like the least upper bound of bottom 0 and bottom 1 is top. And that's the case for pairwise for every two elements in the threshold set. And we need that condition in order to ensure determinism. So, and then you can kind of see over here, we're also allowed to do a read of the first element of the pair, and for that you'd have a differently shaped tripwire. But you couldn't, for example, do a read that would read from both of these, because at the same time you couldn't pass in a threshold set that would be both of these, because that would violate the condition that I just mentioned, where every two elements in the threshold set have to have top as their least upper bound. And you can kind of imagine why, to maintain determinism, that has to be the case, because that would be tantamount to asking, give me whichever element's been written first, the car or the coulter of this pair, I don't really care which. So that wouldn't be okay. So just as an example of the kind of program that you could write in this model, so here, for instance, I've got a pair P that I'm starting out by writing bottom 4 into, and then I have a let par, and there are two sub-expressions in this let par. We're reading from P, and we're putting the pair 3, 4 in. But what we're trying to read out is the 3. So what happens is get first blocks until that 3 has been written. So if we try to run get first, which this is the desugaring of get first down here, so you can see, as I mentioned, get takes an extra argument. It takes the location that you want to read out of, but then it takes this extra threshold set argument, which is exactly this over here. So it takes that extra argument, and then it'll unblock at the point where the state of the lattice gets up above something that it was trying to read. And then at that point, you get your answer back, which is 3, and then you can continue with the program.
Okay, so the threshold set, it's saying it's going to block until in the lattice it's above that set that it's supposed to
At
be.
or above, yeah.
Okay.
So yes, you'll block until you reach a point that is either one of the members of the threshold set or above one of the members of the threshold set, at which point the get will return that member of the threshold set that you are at or above. Yes.
So you can think of the threshold set as a kind of demand that's going to be satisfied.
Yeah. So you know, you're guaranteed that whatever you get back from your get, it's going to be at least that.
Right.
But it could block forever, right?
It could block forever, but it would deterministically block forever. So you could have a program that would block forever in this setting. That's right. But if so, then that would happen on every run. One thing that I didn't mention about let par, I'm not sure if this was obvious or not, but I'll mention it, is that so in a let par, all of the sub-expressions of the let par have to run before we get to the body of the let par. So this in sort of serves as a synchronization barrier in that all of these sub-expressions have to run, but they can run in whatever order. So so we know that when we get to this point, those all have had to have been completed. Okay, so I like to think of because these threshold sets are kind of serve as tripwires. I think of them as allowing you to know when the contents of an Alvar have gone over the line. Okay, so there are two takeaways from the first part of my talk. The first is this point about how monotonicity enables deterministic parallelism, which is an old idea. And then our contribution, which is that monotonically increasing rights combined with these threshold reads give you deterministic parallelism. So I want to talk a little bit about how we went about proving determinism for our language. And the determinism proof had parts that were easy and uninteresting, and it had parts that were difficult and uninteresting, and it also had some parts that were difficult and interesting. So I'm hoping to focus on the latter right now. So this will be an extremely high-level sketch of what our determinism proof looked like for this language. So the property that we wanted was determinism, which is if you start with a particular configuration in our language, it's an expression language, as you saw. So a configuration is just an expression paired together with a store of Alvars. And determinism just says that if you evaluate that expression to its completion, then you're going to get the same thing every time you evaluate it. If sigma evaluates to sigma prime and sigma double prime, then those will be equal. So there are lots of ways to get to determinism. We were kind of starting with the model in that concurrent collections paper I mentioned, and so we set up our proof with a structure similarly to theirs, and they got to determinism by proving a diamond property. And diamond just says that if you start with the configuration sigma and you take one step to two other configurations, sigma A and sigma B, then in one step, those will converge at a third configuration, sigma C. And note that these are just single steps, not the star arrow down here. So this is one way to get to a determinism proof, and then after proving diamond, that kind of does the heavy lifting of the proof, and then you can get to here by doing induction on steps. But diamond's not the only way to get to a determinism proof, and I hope to talk about that a little bit later. But it's sort of an unforgiving way to get there, because these are single steps, and you have to ensure that this is true, even when just taking one step. So we had a lot of trouble proving diamond, actually, and we ran into some difficulty, and we found that in order to prove diamond, we had to prove this other property that I call independence. And so I'm going to, in this next slide, hopefully this won't crash and burn, but I'm going to attempt to explain why we need independence to prove the diamond property. And this is actually the first time, I've given many talks about this topic, but this is the first time I've delved this far into this particular sub case of the diamond proof. So bear with me. All right, so imagine you're trying to prove diamond for a deterministic parallel, or a parallel calculus that you're really hoping is deterministic. And it's June 2012, and the Popple deadline is approaching, and you're trying to get this proof done, and you're stuck on this case, and this is the application case, as so often. So what you're trying to show is that when you start with this particular configuration of a store and an expression, and the expression is an application, you're trying to show that this satisfies diamond. In other words, when this takes a step and this takes a step, then they converge. So without having shown you the operational semantics, this isn't going to make sense. So I'll explain what's going on here. What happens in our semantics is that if you have an application, those two expressions, E1 and E2, they can both take a step. This is a parallel calculus, so they can both take a step in one step. And then what happens is each of those expressions that has taken a step, it could have done some allocation, or it could have written to an Alvar. So the store has changed in each case. So you have a store that's now SA1 and SA2, I'll call on this side. And what you have to do in order to kind of put your whole expression back together after each of those sub-expressions have taken a step is you have to take the least upper bound of those stores. So this least upper bound S here is just the least upper bound operation on that user-specified lattice, but lifted to stores. So you have to be able to do something like this. And similarly, on the other side, you have to do this. So how are we going to make these things converge? Or how are we going to make this work? Well, looking at what we get from the induction hypothesis, we get some information. So we know by the induction hypothesis that if we just had a store and we were trying to step E1, we know that will work. And we know that these converge in some kind of configuration. We don't know what it is. It might be a real configuration, or it might be what we call the error configuration.
Sorry, so what's induction on terms, structured terms?
Yeah. So we might get an error configuration, which is just what happens when you we're allowed to do conflicting rights, and in that case we would go to error. And the error configuration is sort of the configuration where something in the store has gone to top. So so we know both of these things, but now we have to figure out, just focusing on this side of the diamond for a moment, we have to figure out how do we make this this configuration take a step. And so looking at our parallel application rule, we know that we have to step each of these things, EA1 and EA2. And we know that EA1 paired together with this store can take a step. And we know that EA2 paired together with this store can take a step. But we're not starting in either of those stores. We're starting in this bigger store that has this other thing we stepper bounded onto it. So we're in the case of EA1, we have this extra thing tacked on here that we have to deal with. And in the case of EA2, we have this extra thing tacked on here that we have to deal with. And this was a problem. That's why we ended up needing to prove this property that we call the independence property. We have to be able to tack on this additional piece of store and know that this expression can still take a step. And so if you're familiar with...
So isn't there a kind of monotonicity idea going on there where if you can tack on extra stuff, if you can make a step and you can tack stuff on, you should also be able to make the same step.
Right. And I was actually kind of happy when we ran into this issue in the proof because it seemed like it was all boiling down to something really important here. So we had to prove this property that we called the independence property. And independence, I've left out some side conditions here. So this is the simplified version of the independence property. But what it says is that if you have a configuration and it can take a step, then you can bring in a configuration from the outside, subject to constraints. That's what the side conditions are that I've left out, and you can take a step that looks like this. So I happened to be working on this kind of a little less than a year ago in the spring, and I was visiting a mall at Northeastern, and I was telling her we'd figured out that we needed this independence property, and I wrote it up on the board, and she said, that looks kind of like a frame rule. And I didn't really know what she meant at the time. In the meantime, we were kind of busy with finishing the proof and writing the paper, and I didn't really come back to this idea until much later this fall, when it kind of started nagging at me again. But it turns out that, of course, she was absolutely right. So I'll talk for a second bit about the frame rule. So the frame rule is an idea from separation logic. And what it says is that, let's say that you're trying to run this command C, and you're starting with this precondition P on the heap, let's say. Well, if you have this for triple, if you know it's the case that starting in P, executing C lands you in a situation where the postcondition Q obtains, then, and again, I've left out a side condition here to make this slide pretty, but it's the case that if you take P and star it, or separate and conjoin it with some other piece of state R, then and run C, then at the end you'll come out with the original postcondition Q again starred with R. So I read about the frame rule for the first time years ago, but I always imagined that the frame rule was, I kind of thought that the idea of the frame rule was that if I'm running a command and it only uses up this kind of this one piece of resources, then I can be sure that this R will be left intact at the end. And I thought that that was all the frame rule was about. I thought the point of the frame rule is leaving R intact as long as it's not part of the footprint of the program. But this independence lemma that we had to prove kind of gave me an interesting new perspective on the frame rule. Because here, well, I'll talk about the frame rule again for a minute. So there's another thing that you know from the frame rule. First, you know that R is intact, but you also know that Q is still the case after the frame rule. So in other words, you can show using the frame rule that you won't interfere with other people's state, that's R. But it also shows that other people won't interfere with you, and that's Q. And it was that other people won't interfere with you side of it that that was really kind of key to what was going on here. Because here, what we have is, if you have this store and it steps to this other store, and you have E stepping to E prime, then if you add this piece of extra store, S double prime, subject to some restrictions, then not only will you end up with S prime, S double prime, least upper bounded together, but you'll end up with the same E prime that you would have before, just running in the individual, in the S prime by itself. So that was really important, because the fact that this E prime and this E prime were there, that was what let us prove determinism.
So just going back to that intuition, which
Yep.
like, is there also an intuition that's maybe kind of slightly different to the frame rule? In other words, that if you're adding something to the store, that might allow E prime to have kind of made more progress in some sense than the other. So let's say the bottom one was, E, in other words, rather than going to E prime, you would go to E double prime, which was still related to E prime in some way, but it's
Make more progress as in, like, allow a get to unblock or something like that. Maybe. I hadn't thought a lot about that side of it. Do you think that, is this like a property of the independence lemma, do you think, or something else?
Well, I'm just wondering if the intuition seems to be that you can kind of, you've got a store in which a computation can proceed, and you're saying that if you kind of add monotonically to that store, then the computation can still proceed. But the intuition seems to be that if you add to that store, you might add information that would allow more output instances.
But also might restrict more, because you can't put. Right. In other words, if S double prime adds information about if it takes a variable from bottom to 3, then now if E were trying to put that variable, then that wouldn't.
Yeah, it might restrict also.
It might restrict the.
So the restrictions, I guess I keep saying subject to some restrictions, so I left the side condition out because it's kind of a pain to explain. But the restrictions on S are that it can't say anything about variables that were allocated, not written to, but allocated between S and S prime. But it is allowed to say things about other stuff. It can say stuff about anything that was in S to begin with. Another thing to point out here is that there are kind of two versions of this. There's this one where you step to this, and there's another one where you step to error. And we can show that if you step to error up here, then you're going to step to error down here. So maybe that has.
Actually, no, so now I am confused. Actually.
Okay.
Sorry. Even with that restriction, though.
Yeah.
If E were putting, what is the semantics of put? When you put, is it given? If you put, if you write to an E bar that's already written to, does you get an error?
So I guess I forgot to mention the semantics of put are that when you do a write, what you're trying to write and what is already in there get least upper bounded together. So.
Right, but what I mean is, so suppose E were putting, suppose that S had some variable X, which was bottom. And E puts X 3.
Okay.
Okay. And then suppose that S double prime says X actually is going to be equal to 4. Right, that would not be conflicting in the way that you described, because it only affects the existing variables in S.
So in this model, is it possible that can we reassign X to 4? Because X is already 3 in the lattice, you can't again reassign.
Well, if you assign X to 4, then you'll step to.
Okay, so there's a restriction that I'll have to bring up the paper to show you the exact side conditions on this, but there's a restriction that you know that this, or rather that this least upper bound is not top.
That least upper bound is not top. Okay,
Yeah,
right,
and if this one isn't top, then nor is this one.
Yeah.
So that I think that would rule that out. Okay, so really, kind of this slide is kind of the whole reason I'm at MPI this week, because once I noticed that this analogy could be made, I started talking to Neil and Aaron about concurrent separation logic stuff, and we started thinking about that. And so now we're kind of in the process of coming up with a separation logic like logic for deterministic parallelism. And I'm really excited about that. So that's most of what I have to say. There's a lot more information to be found in our tech report. There you can find the syntax and semantics of our Alvar language. the proof of determinism is in there. We talk a little bit in an informal way about subsuming other deterministic parallel models. And then one thing I haven't really talked about at all is kind of letting in some controlled form of non-determinism. And this is actually something, this last point is something that we've kind of been talking about a lot, because the fact is that these restricted gets, where you can only read a limited amount of information about the state of an Alvar, that's really pretty limiting. But a form of controlled non-determinism where you can do exact reads, or we call them destructive reads, of the state of an Alvar. This lets in a form of, we can implement this in such a way that this lets in a form of non-determinism that admits errors where the program could raise an error, but never a wrong answer. And we do that by, once we do one of these destructive reads from an Alvar, you can easily implement it by then corrupting the state of the Alvar so that if anybody else tries to read from it at that point, then they go to top and it's an error. So we think that there's actually maybe more to be done in this support for controlled non-determinism thing, and maybe we can come up with some interesting constructs that are good for practical programming. So if you're interested in that, I'd love to talk to you about it. And I hope that my talk has convinced you that in our setting, determinism abides. And I'd be happy to take questions.
So the monotonicity, it's the monotone functions we're describing were the like the get and the put interacting with the lattice. Is that it?
So for a while I thought that it was that get and put were the monotonic functions. What I can say about put is that it's inflationary in the sense that when it does a write, the position of the variable it's in is always going to be at or higher than the position it was in before in the partial order, because of the way put is implemented, where it always takes the least upper bound of what's there and what you're writing. So it's inflationary writes. So you could also imagine a sort of a situation where put is the monotonic function, and for a given two stores that are in different states, but or let's just say Alvars. So given two Alvars that are kind of in different states, but states that have an order, if you did puts to both of those, then you would come out with two Alvars that still have that order. So I think put is also monotonic in that sense, if that makes sense, like it preserves the ordering that they had. But I was thinking of the monotonicity being more of like this mapping between the ordered set of program configurations and the ordered set of states. But that was kind of the other form of monotonicity that I was thinking of. So maybe there are actually like two orthogonal notions of monotonicity here. I'm not
Okay, because
sure.
you're saying if this configuration, like small steps to this one, then the heap gets strictly.
If there's a marker, then I can talk.
Yeah, it's right up on top of the.
Yeah, so if you had a pair, this pair, and then you wrote the 4 into there.
We can't read that. Is there a marker over there?
There's a pen or something that would do it.
Not the wall. This is green. On the table.
Okay, we'll try this. So maybe I'll use this piece of board here. So imagine you started with a pair.
Can you see that in Kaiser?
Yes, they can.
Yes, we can.
Good.
Success.
Okay, maybe I'll write even bigger. So if you had a pair.
That's too big.
I'll write smaller. So you know that that's less than or equal to this in the partial order. And you also know that say And so if the function that is the monotonic function here is the function that writes 3, I guess, maybe I've done this backwards, but I guess my point is that if this ordering holds, maybe I should have done it like this, actually, or rather. Okay, so here, here we've written 4 into the pair, and here we've written 4 into the pair. But in one case there was a 3 already there, and in the other case there wasn't. So if this is the one that has had the monotonic function f applied to it, where f is the function that writes 3 into a pair, then you can see that the ordering is preserved by applying f to the pair. That's kind of what I was striking at.
But these two also have
Yeah. So it's also still the case that this is true.
Lindsey, in this example, would you expect the function to also preserve joins?
Good question.
In this example, you would expect.
Well, in this example, yeah, I don't know about in general. But yeah, that's the idea that the put function. I guess this is actually put 3 is sort of the name of this function. So in that sense, at least in this example, put 3 is a monotonic function. So does that help answer your question?
Yeah, I mean, I was just wondering if in general these functions are kind of like the functions that are characterized by evaluation. Essentially. I mean, like evaluation is a function from configurations to configurations.
So maybe the functions we're actually talking about is the evaluation function.
Right. And if that preserved joins, then you'd be able to say something nice if you have lattice, right?
Right. Yeah, I guess I need to do a little more thinking about that. But yes, any other questions?
Yeah, so in the beginning you said, right, the IVAR model is incomplete. So,
Right.
Yeah, so this case also is incomplete. Only thing is now it is, the incompleteness is generalized to Alvars.
Right. Yeah, so that's a really good point. So I guess I'll move back over. Well, where can I stand? Where will you be able to see me?
There.
I'll stand here. So sorry to make you all turn sideways, but it would be a nice thing, wouldn't it, to have a model where you could write all deterministic programs.
Yes.
And I don't know if such a model is even possible, actually.
Right.
But we can kind of get like incrementally closer to being able to express more and more. I don't even know how you would go about designing a model where you could write all deterministic programs. That would be interesting.
Yeah, you're right. Soundness is of interest here, but not the completeness.
Right. But we thought that the kinds of programs that you couldn't express were kinds of programs that you might really want to try to be able to express, which is what kind of motivated us here. So we still have something that's incomplete, but we hope it's more complete in a way that is useful.
Yes. You're definitely pushing the envelope. So from IVAR to LVAR and incomplete.
All right.
Did you have to restrict your model in order to prove independence, or did it just fall out to you?
That was the interesting thing. Once we set up our model in this way, the independence lemma kind of fell out of it, and so we hadn't been trying to prove a frame property, but one just sort of fell out, which is what was really interesting to me. That kind of just happened. Not intentionally, I guess. So that's kind of what makes me especially excited right now, wanting to look at separation logic for determinism. All right.
So another question. The main idea that you were saying, how monotonicity enables the deterministic parallelism. So it's the fact that because anytime I take a step, I know that the heap is going up in that lattice. That's why everything is deterministic.
Right.
But in the case, in like the bad examples you showed right in the beginning, why exactly was it not monotonic?
Well, it is monotonic, according to some partial order. But the kind of what they had was a sufficient condition for monotonicity but it didn't express all the monotonicity, I guess. Does that make sense? Like, they had monotonicity.
But because they had an Alvar, they had some notion of the order.
Right. So their monotonicity was this very sort of ham-fisted notion of monotonicity, where stores were always growing. Every time you did a put, stores were always growing. Their domains were always growing. So that's certainly a notion of monotonicity, which is why our model can express Alvars. But it's not the most subtle notion of monotonicity that you could have. So it doesn't say anything about the values of those variables in the store, those store locations, for instance. So if you want to talk about the relatedness of values in the store, then you have to have a more interesting definition, or a more subtle definition of monotonicity, or a more subtle partial order, which then gives rise to monotonicity. So.
And how do you envision, if this were in some programming language, how do you envision actually supplying these partial orders?
Yeah, so in our model, the whole thing is parameterized by this lattice that you pass in. And so we require that it has to be a joint zone lattice. That's the only requirement that we have of it. Now, in a real setting, you could imagine providing a library of data structures whose states form a lattice. And actually, people have done this, which is really cool. There are people working on distributed database stuff who have developed this language for distributed database programming. And what they're trying to ensure is not monotonicity, but rather this notion of eventual consistency, which is that all the nodes in a distributed database will eventually agree. And but that's kind of also based on the notion of monotonicity. And so they ended up actually doing something very similar to what we're doing, which is parameterizing by a lattice, and they supply this library of concurrent data structures that you can plug into their system. They also let you specify your own. So there's a type that an interface that you have to conform to. Now, you could also imagine, as I pointed out, if you try to do a read, a get, and you pass in a query set that doesn't, a threshold set that doesn't meet the threshold set restrictions, then you break determinism. So that, in our setting, that's important. In their setting, they don't have to do that because like I said, they're not trying to ensure determinism. They're just trying to ensure eventual consistency. And when you do a quote-unquote read in one of their settings, all you're doing is kind of reading nodes from different places in the distributed database and then taking a least upper bound of them and kind of putting them into your own local copy. So it's not so much a read as like a put to your own copy, which you then get to kind of observe unrestrictedly. So they don't have this kind of this notion of threshold reads that we have to do because we're kind of in a different setting.
How do you actually represent that threshold set?
It's a good question. So the implementation that we have right now is just a PLT Redux model. And the kind of lattices that we've plugged into it are not very interesting ones. So for instance, that lattice that you saw, that was the just the natural number lattice that goes straight up. This one, threshold sets in this are always singleton sets, because that's the only incompatible threshold set that there is. You can't pass in two elements of this because then they would have a least upper bound that wasn't top. It would just be the max of them. So threshold sets in that setting are really easy. But some of these other settings, it could be really weird. So that's actually a really good question. I don't know yet what the right way to implement threshold sets efficiently is. All right.
Any questions from Kaiserslautern? Ye old Kaiserslautern?
I guess I'll stand over here again.
Hello.
Yes, sorry, we're muted.
Yeah.
Are there any questions?
Yes, but we're sort of answering our own questions.
Sorry.
Yes, okay, so in the counter case, sort of, it seems sort of the only read operation you can make is wait until the counter reaches a certain value.
That's right, yeah. So reads aren't very interesting in that case. You can, when you do a read, the information you get back is you've surpassed 3 or whatever. That's not, you know, so you can imagine using it as a sort of synchronization variable in a program, but you don't get a lot of really interesting information back in that sort of a read.
Yeah.
Okay, thank you so much.
Thank you.